Have you ever stood in a building on a freezing cold day and wondered how it stays so perfectly warm? Well, it's not magic. It's actually this incredible system of, well, you can think of them as invisible rivers, flowing right inside our walls and under our feet. Today, we're going to dive into this hidden world and see exactly how hydronic heating works.
So let's start with a big question, a real engineering challenge. How in the world do you heat a massive skyscraper 100 stories tall? I mean, trying to push hot air all the way to the top through these enormous ducts would be a nightmare. It's super inefficient and would take up a ridiculous amount of valuable space. So what's the better way?
Well, the answer is water. It's as simple as that. Look at this comparison. Heating with air, you need these huge, clunky ducts. But hydronic systems? They use these sleek, space-saving pipes. And that's all because of a basic rule of physics. Water is just unbelievably good at carrying heat. It can absorb it, hold onto it, and move it around way more efficiently than air can. It's a total thermal superstar.
And that gets us to the core of what we're talking about. Hydronic literally just means heating with water. And to really get our heads around it, we're going to do something kind of fun. We're going to follow the journey of a single water molecule all the way through a complete system, from the second it gets supercharged with heat to the exact moment it delivers that warmth to a room. All right, let's begin that journey. In this first part, we're going to take a bird's eye view of the whole system. We're going to break it down piece by piece, just following the flow of water to see how every single component plays its part in keeping us comfortable.
Okay, this diagram right here, this is our roadmap. It shows you all the main players at a glance. You've got the boiler, that's our starting line. You've got the pumps, which get everything moving, the pipes, which are like the highways, and then the terminal units, the radiators. That's the final stop. So let's start with the energy does, at the heat source. So now we get to zoom in on the real powerhouse of the system. We're going to focus on the parts that actually create the heat and then, crucially, get it moving. You can really think of this as the building's heart and its circulatory system. So our water molecule's big adventure begins right here, inside the boiler. This thing is the heart of the whole operation. It doesn't matter if it's burning natural gas or using electricity. Its only job is to pump a massive amount of thermal energy into the water, heating it up and getting it ready for its long trip.
But here's the thing, hot water isn't just going to move by itself. That's where the pump comes in. The pump is the engine. Inside of it, there's a part called an impeller that's spinning like crazy. It grabs the water and uses centrifugal force to sling it outwards, converting all that motion, that kinetic energy, into steady pressure. And it's that pressure that literally shoves our water molecule through thousands of feet of pipe.
So our water is now hot and it's under pressure. It's officially entered the system's lifeline, this huge network of pipes. Seriously, think of them as the arteries and veins of the building. But moving hot water through a sealed system like this creates some really interesting challenges that engineers have to be pretty clever to solve. Let's rewind for a second, back to high school physics class. What's the one thing we all learned about what happens when you heat water? It expands, right? Now imagine that happening inside a sealed system of solid steel pipes. That expanding water has nowhere to go. And without some kind of safety valve, the pressure would just build and build to really dangerous levels.
And the solution is this brilliant little device, the expansion tank. The best way to think about it is as the system's long. It's a small tank that has a cushion of air inside, usually separated by a rubber diaphragm. So as the water gets hot and expands, it just pushes into this tank, compressing the air. It gives that extra volume a safe place to go. And just like that, problem solved.
Now for another challenge. How do you make sure every single room gets a fair amount of heat? Well, if you use a simple setup called direct return, the water takes the easiest path. So the first radiator gets blasted with hot water and the last one gets what's left over. But engineers came up with a genius solution called reverse return. Check it out. The way they route the return pipe ensures that the total distance the water travels to the radiator and back again is exactly the same for every unit. Sure, it takes a little more pipe, but the result is a perfectly balanced system where everybody gets an equal share of the warmth. It's just smart. Okay, our little water molecule has done it. It's traveled through the building's arteries, it's navigated that clever piping system, and it has finally arrived at its destination, the room that needs the heat. Now it's time to complete the mission. So how does that heat actually get out of the water and into the room? Well, there are two main ways. The first is what we call natural convectors. Think of the baseboard heaters you see in a lot of houses. They work on simple physics. The hot fins warm up the air around them, that air gets lighter and rises, and that naturally pulls cooler air in from below. The second way is with forced convectors, which use a fan to literally blow air across the hot coil. And because that fan speeds up the heat transfer so much, the system can get the same job done with much cooler water, say 120 degrees instead of 160. That can make things a lot more efficient.
So, when you adjust your thermostat, how does that actually work? It's sending a signal to one of these guys, a control valve. You can just think of it as a super precise automated faucet. When your thermostat says, hey, it's too cold in here, the valve opens up and lets hot water flow into the convector. The second the room hits the right temperature, the thermostat signals the valve to close, stopping the flow. It's this simple, elegant little dance that gives you perfect temperature control.
So we've seen all the individual parts, but this brings up a really important question. How do engineers actually design these systems? How do they know exactly how much water they need to move to deliver the right amount of heat? Well, it all comes down to a single, beautiful formula, a golden rule that governs every hydronic system ever made. And this is it. This is the golden rule of hydronics. Now, I know it might look like scary math, but it's actually incredibly simple. Q is just the amount of heat we need, and it's measured in BTUs per hour. A BTU, by the way, is just a standard unit of heat. GPM is the flow rate. How many gallons per minute are we pumping? And that triangle T, delta T, that's just the temperature difference between the water going in and the water coming out. This one formula ties everything together: heat, flow, and temperature. It's beautiful.
Let's make this totally real with an example. Okay, let's say you're designing an in-floor radiant heating system, and you needed to deliver 10,000 BTUs of heat per hour. That's our Q. The engineers decide that the water should cool down by 20 degrees Fahrenheit as it moves through the floor. That's our delta T. So you just plug those numbers into the formula, do a tiny bit of math, and boom. The formula tells you that you need to pump exactly 10 gallons of water per minute through that floor to hit your target. It's that precise.
And there you have it. That completes the journey, from the boiler, through the pump, through all those pipes, delivering its energy, and then heading right back to the start to do it all over again. This invisible river of water is what keeps our buildings comfortable and safe. And it really makes you think, doesn't it? What other invisible, essential systems are working all around us every single day just to keep our world running?